Hi, I am Siddharth, and I am going to talk about active safety envelopes using light curtains with probabilistic guarantees. Consider this scene that contains many obstacles. If a robot has to navigate safely, it must estimate the safety envelope of the scene. The safety envelope is an imaginary surface that separates the robot from all obstacles in its environment. As long as the robot never intersects the safety envelope, it is guaranteed to not collide with any obstacle. How can the robot estimate the location of the safety envelope? A common strategy is to use LiDARs, but LiDARs can be low resolution, expensive, and slow. In contrast, a programmable light curtain is a recently invented sensor that is much higher resolution, cheaper, and faster. The user selects a vertical 2D surface, and the light curtain detects objects intersecting that surface. Therefore, light curtains present a challenge. They require the user to select which locations to sense. Suppose we have a scene with no prior knowledge of where the obstacles are. How should we place light curtains to find them? One strategy is to place curtains at random locations in the scene. We will see shortly that it is incredibly hard for obstacles to avoid getting detected by random curtains. Next, assume that we have estimated the safety envelope in the current time step. As obstacles move and the scene changes with time, we wish to estimate the envelope for the next time step. In this case, it may be inefficient to use random curtain placements. Instead, we train a neural network to forecast how the safety envelope will move, and we place light curtains to sense the predicted locations. At the same time, we place random curtains to discover obstacles and update our predictions. Finally, the light curtain measurements are input to our method, closing the loop. Can we do any theoretical analysis on the probability of random curtains detecting obstacles? First, we need to account for the physical constraints of the light curtain device. These are encoded in a constraint graph, where nodes represent locations where the light curtain might be placed. An edge exists between two nodes if they can be imaged sequentially while satisfying velocity and acceleration constraints. This is the full constraint graph. So, any path in the graph represents a feasible light curtain. We can generate random curtains by randomly sampling paths from the graph. Let's say that we are given the shape, size, and location of the obstacle. Some random curtains will intersect and detect this obstacle, but others will miss the obstacle. Can we compute the probability of detection? A naive approach would be to consider all feasible curtains and add the probability of sampling the curtain if it detects the obstacle. Unfortunately, this is impractical because the number of feasible curtains is exponentially large. In the paper, we show that we can exploit the structure of the graph and use dynamic programming to compute the detection probability in only a single pass through the graph. Let us look at an example. The x-axis shows the time taken to place multiple random curtains, and the y-axis shows the detection probability. As more curtains are placed, the probability that at least one of them will detect the obstacle increases. In about 70 milliseconds, random curtains are able to detect an average-sized pedestrian with more than 95% probability and an average-sized car with more than 99% probability. Please check out our interactive web demo of random curtain analysis on the project website. Here's our method in action. The middle video shows the light curtain and a LiDAR point cloud for visualization. The right video shows light curtain intersection points across multiple frames. The scene contains two pedestrians walking in complicated, overlapping trajectories. The light curtain is able to accurately estimate the safety envelope and produce a large number of intersections. Due to the guarantees of high detection probability, our method generalizes to 5 pedestrians walking in the scene. The motion of the pedestrians is correctly tracked across time. Our method can also handle extremely fast and sudden motion. In conclusion, we show that random light curtains can discover obstacles with high probability guarantees. We combine this with a machine learning-based forecasting method to efficiently track the safety envelope. This is a step towards safe robot navigation using inexpensive, controllable sensors. Please visit our website for more details. Thank you for listening.